Okay, thank you so much. My name is Yirga Abebe. I am a postdoc student at Naresuan University, Thailand. So today I will be talking on our paper on the title Halpern method for solving perturbed double inertial Krasnoselskii Mann iterations and its applications in image restoration. This was a work done with my colleagues at Naresuan University. So my talk basically consists of the introduction, main results, application, and some conclusions and the way forward. To begin with the introduction, here we have some basic definitions on the Hilbert spaces, the norm, the inner product, and so on. And as we are going to mainly talk on the fixed points, we define the fixed point here. And there are some types of mappings like the non-expansive mapping, which satisfies the inequality given by 1, quasi-non-expansive mappings, a mapping which satisfies the inequality 2, and the monotone mapping. And there are also another mappings. So here we can easily see that the definition of quasi-non-expansive mappings includes the non-expansive mappings. Actually, the set of fixed points of quasi-non-expansive mappings is non-empty. From its very definition, quasi-non-expansiveness starts from the non-emptiness of its set of fixed points. So to come to the fixed point applications, we have many applications of these fixed point theories in economics, physics, and so on. That's why we intend to study about approximation of fixed points of these basically nonlinear mappings, but in practice we encounter these linear and easy mappings in this case. And in particular, there are several iterative methods which have been studied by researchers like Edelstein, Aksum, and Inwa. One of the most famous and oldest fixed point iterations is the Krasnoselskii Mann iteration. And we sometimes call it actually Mann iteration type, Mann type iteration. So it's given by like the iteration in number 4. Here, it was meant initially for non-expansive mappings, but through time, researchers have been developing it into some more general types of mappings. On this Mann type iteration system, iterations, many researchers have been doing or approximation of fixed points of these types of mappings. For example, Moalen and Gerges, Perturbed. For Perturbed, as you can see, it is very recent work. For the literature review, we start by the work done by Moalen, which is given by iteration number 5. So in this iteration, as you can see, they have included the inertia, which was introduced by Polyak. So the inertia helps the iteration to converge faster than the non-inertial version. This is one of the improvements of the Mann type iteration, but this works only for quasi-contraction mappings. So it was improved by this Gerges in 2023, like the iteration given by 6. Here they have 2 inertial steps, and this is like a Halpern type. They started with Mann type, and then they ended up with Halpern type, and they proved the strong convergence of the method for non-expansive mappings in this case. And there are some assumptions also, like these assumptions, which are assumed to be strong assumptions. And recently, Cortil and Peppocket in 2025, actually, they introduced a Mann type iteration, which involves two inertial steps and which works for quasi-contractive mappings. This class of mappings is actually a narrow class of mappings. And here, what they did was they added some perturbation parameters, like you can see in iteration number 7. So they proved the convergence of the system to the fixed point of this Tn, where Tn are the quasi-contractive mappings. But here the strong conditions on the perturbation parameters were introduced or imposed, like these perturbation parameters are assumed to be in L1. So based on this works, we propose some, if we can extend the category of mappings to more general category, and the conditions can be relaxed. So what we did was, like, we have extended the mapping to quasi non-expansive mappings. Like I said before, they were working on quasi-contractive and non-expansive mapping. So we extended the map to be quasi non-expansive mappings. And here we have some more standard assumptions, C2, C3, C4, and C5. In C5, they are the perturbation parameters, and they don't need to be in L1. They don't need to be in L1. So the condition here, C5, relaxes the condition which is in imposed here in Cortil. So with these assumptions, we introduced our algorithm like this. Here we have two general steps. The first step is for the inertial steps, and the second step is a set of iterations for which takes us to the Halpern type iteration. Here we have two steps for the inertia. And we have also these perturbation parameters. So throughout the study or in the experiments, we will also compare how these perturbations will affect our algorithm. So what we did was we proved the convergence of the theorem first. It converged to the fixed point of the mapping T under the assumption C1 through C5. Actually, the proof was very long, so I couldn't bring it here. But what we did was, like, we first proved the boundedness of the sequence generated by this algorithm 8 to 9. Then we used some existing relations and lemmas together with the boundedness of the sequence to prove the strong convergence of the method. So after convergence, what we did was, like, we provided an example. This is an example of quasi non-expansive mapping, which is not non-expansive actually, just to provide an example, which is quasi non-expansive, but not non-expansive. And to clarify or to show that our method is more general than the previous ones. So this is the explanation or the proof that it is quasi non-expansive. We have shown here that it is not non-expansive. And here we have 0 as a fixed point of the given mapping. We took some standard parameters which satisfy the conditions already stated in C1 through C5 of the algorithm. So every condition for the algorithm is satisfied. So here we let this En, the capital En, to be the error term sequence. Like, UN is the sequence of iterations, and P is our fixed point, like it is given here, it is 0. So we will calculate the convergence of the iterative methods using using these visualizations. The first figure shows the inertial versus non-inertial version of the algorithm, just for our algorithm actually. The second one shows how the perturbation parameters affect the algorithm, the convergence of the method. So here, as you can see, the red one shows the convergence of the method without perturbation, like taking the perturbation parameters to be all 0, whereas the blue one here shows in the existence of the perturbation parameters, which means taking all to be non-zero. So still the algorithm converges, but as you can see, the version of the algorithm without the perturbation is faster than the one with perturbation. We have also tried to compare the algorithm with the existing results in the literature, like with Abebe and Cocktail. We have also included one more for Moalan. So for this comparison, we took a contraction mapping. Actually here, why we took contraction mapping is because the mapping involved here in the work of Cocktail is contraction mapping. So in order to be convenient for the comparison, we took the same type of mapping and all parameters equal. So we found this visualization, like as you can see in the label here, the red one is the convergence of our algorithm, the black one for the CP, for the Cortil, the blue one is for the Moalan, and for the magenta one is for the Gabriel algorithm. So generally, this shows that our method is faster than the methods existing in the literature actually. So after comparing our methods, we come to some specific application of our work of image restoration. So when we restore images, first we need to have a blurred image. What do we mean by blurred image? Blurring is a process by which a given image becomes less sharp or not clear, not clean. So by different types of causes, maybe it can be by camera check, movement of the object under consideration, defocus lenses, and other factors like wind, light, and so on. So to be specific here, if we have given a clean image U, this image U is in Rn, actually in finite dimension. Reading the image, then we have a blurred image nu here also. Then we can relate them by equation 10. Like nu is a blurred image. Here, big A is the blur operator and omega is noise. So the issue is how can we find the clean image from this blurred image? So we have a standard optimization problem for image restoration, which is given by the minimization problem in 11. So here we have the minimization problem with least square problem plus the L1 regularization. So minimizing this problem is equivalent to solving the monotone inclusion problem in 12. These are equivalent actually, but we need to bring this relation, or we need to bring to our fixed point relation. So this one is exactly the same as solving the finding the fixed point of this proximal operator given by 30. You see, here we have, this is the guiding one. This is the guiding one. So our point x star is a fixed point of the proximal operator if and only if it is zero of this f plus g, where f and g are like given here. F is the gradient of, the gradient of this one, and g is the subdifferential of this one, because this is differentiable generally. So what we are saying here is solving this fixed point problem is exactly the same as solving this minimization problem. So if we solve this fixed point problem, it means we have solved the image restoration problem. So for this, what we did was we took some clean image of a mandrill and a butterfly. Then we apply different types of blurs. Like in this case, we took 4 blurs: average blur, disk blur, Gaussian blur, and the motion blur. So the next step is to remove these blurs and recover the original image. So here we are given this original image, like the mandrill in figure 3. So figure A is the original image of the mandrill. This is the degraded image. As you can see, it is already distorted. So we applied our algorithm and the algorithm of the methods in the literature actually to restore the degraded image. So as you can see here, the first image shows the image restored by our algorithm. The next one is the image restored by the GK algorithm, is for the Georgis actually. And the last one, C, is the image restored by the MFP algorithm. So I think you can observe the difference. For me, it is clear. Maybe I'm not sure whether you can identify the difference. The first image is to some extent more clear than the image restored by GK and MFP. So in this case, our method is more, better than the existing results in the literature. We have also the original image for the butterfly as image figure 5, so figure A. This is the original image, and the one in the next is the degraded image. This is degraded by the disk blur actually. So here we recovered the images using our algorithm. The second one is by GK algorithm, and the third one is by Molan algorithm. So it can be seen actually clear. For me, it's clear. I'm not sure if you can identify the difference. But since it is not this seems objective, we have employed some metrics to evaluate the quality of the images. We have 2 metrics here: the improvements in signal to noise ratio and the SSIM index. Here we put them like in formula 14 and 15. So here we have some parameters U, Nu, and UNR. Here, for example, U is the original image, Nu is the degraded image, and UN is, you see, the iteration. the iteration. We are trying to recover the image through the iteration. So at the end step, we have the UN image. So we use this matrix to measure the quality of our image. Actually, this SSIM is like similarity. It is structural similarity. It ranges from -1 to 1. Values which are close to 1 have better quality of images, and values which are below 0 are assumed to have less quality images. For the ISNR, as the value of the ISNR increases, the quality of the image is assumed to be good. So the result of the experiment shows, like for the 4 blur types: average, disk blur, Gaussian blur, and motion blur. So for the 3 algorithm 3.1 here, GK algorithm, and MFP, we have here, for example, the red ones are for the SNR, and the blue ones are for the SSIM. So as you can see, for example, in the first one, we found the ISNR value for our algorithm to be, excuse me, to be 4.4 something. And here the ISNR for GK algorithm is 1.8. And for the MFP algorithm, we found it to be 2.7. So you see, we were not able to clearly identify here the difference, but using the scientific or quantity, we can judge that our method is better than the existing ones in the literature. Similarly, for the SSIM, here we found it to be 0.8, which is very close to 1, and here 0.7, here also 0.7. You can see the difference for the other motion blur, Gaussian blur, and this blur similarly. This table also shows for the motion blur, only for the motion blur across the 3 algorithms. Here we have 8.75 for our algorithm, 4.5 for GK, and 6.3 for MFP. So it can be observed that even with different lengths of kernels, these are the lengths of the kernels, 3 pixels, 9 pixels. So our method outperforms the other methods. So when we come to the conclusion part, just what we did was, like, we introduced a Halpern type method for solving the Krasnoselskii Mann iterations. We proved the strong convergence of the method. We also provided some numerical examples to show the convergence of the algorithm, and we introduced or we explored some applications of the method, and we just showed the performance of the method against the results in the literature. So generally, our method outperforms the ones in the literature. Here what we did was, like, we imposed the blur operator and we deblur. So the next work is that, and which is not actually an open problem for still, as to my knowledge. If we are given some blurred images and we are asked to identify the type of blur associated with the image, I think it's not done yet. So for the future, I'm planning to work to identify the type of blurs from a given degraded image. So this research was funded by Naresuan University. Thank you so much. If you want to read my paper, this is already published in the International Journal of Mathematical and Computational Sciences, Bangmod.